Hey, welcome to the Explainer. Today we're jumping into one of machine learning's most elegant and honestly powerful ideas, the support vector machine, or SVM for short. At its core, it's all about one thing: finding the absolute smartest way to draw a line. Okay, let's start with a bit of a puzzle. This quote gets right to the heart of a huge challenge in AI. How do you teach a machine to generalize? To see the big picture, the forest, instead of just memorizing every single tree it's ever seen. And that right there, that's what we call the classifier's dilemma. In the machine learning world, you'll hear fancy terms for it like the bias-variance trade-off, but really it boils down to the problem of overfitting. So you've got two extremes, right? On one side, a model can overfit. Just like that botanist, it gets so bogged down in the tiny details of the data it trained on that it completely fails when it sees something new. But on the other side, it can underfit, meaning it's so simple it misses the main pattern altogether. The real goal, the sweet spot, is finding that perfect balance right in the middle. All right, so let's make this super simple. Imagine we have two groups of dots on a chart, and we want a machine to learn how to tell them apart. Well, the easiest way to do that is to just draw a line between them. Everything on one side is in group A, everything on the other is in group B. Easy enough. But here's where it gets really interesting. Technically, you could draw an infinite number of different lines that separate those two groups. So how does the machine pick the optimal one, the one that's going to do the best job when it sees new data it's never encountered before? And this is where we get to the first really brilliant idea behind support vector machines. It's this concept of the maximum margin. An SVM doesn't just look for any line. It searches for the line that creates the widest possible street or buffer zone between the two groups. So how does it find this widest street? Well, it doesn't just draw a line. It builds what's called a separating hyperplane. Now, hyperplane sounds super complicated, right? But don't worry. It's just a fancy word for the decision boundary. In 2 dimensions, like we're seeing here, it's just a line. In 3D, it's a flat plane. Any higher than that, we just call it a hyperplane. It's the divider. And this is the absolute key. The SVM finds the boundary that is as far away as possible from the nearest data points in both groups. That empty space, that buffer zone you see between the dotted lines, that's the margin. The entire goal of the SVM is to make that margin, that street, as wide as it can possibly be. But here's the really clever part. In this whole process, most of the data points, they don't actually matter. The only ones that do are the points that are closest to that hyperplane, the ones sitting right on the edge of the street. And we have a special name for them: support vectors. Just look at those circled points. Those are our support vectors. And get this, they are the only points that define where that boundary goes. You could literally delete every other data point on the chart, and that line, it wouldn't move an inch. It's held in place or supported entirely by these most critical points. So what's the bottom line here? Why go to all this trouble to find the widest straight? Because by maximizing that margin, the SVM creates a boundary that's more stable and less sensitive to the random noise in the training data. This makes the model way more robust and gives it a much better shot at getting things right on new data. Now, this widest street approach is fantastic when your data is laid out nice and neat. But what happens when the real world gets messy? What if the data is all jumbled up and there's just no way to draw a single straight line to separate the groups? And this is where SVMs go from being just plain clever to seeming like actual magic. It's a little something called the kernel trick. So instead of trying to draw some crazy, curvy, complicated line, the kernel trick does something kind of mind-bending. It uses a special math function to project the data into a higher dimension. And the magic is, in this new, higher dimensional space, the tangled up data often becomes perfectly separable with a simple flat plane. The best way to think about it is like this. Imagine you have a bunch of red and blue dots all mixed up on a flat sheet of paper. You can't draw one straight line to separate them. But what if you could just lift that paper up and bend it? All of a sudden, from a new 3D perspective, you could easily just slice a flat plane right through the middle, cleanly separating the reds from the blues. That's the kernel trick. And here is the beautiful result. That simple, flat slice you made in that higher dimension, when you project it back down to our original flat view, it becomes this elegant, non-linear curve that perfectly carves out a boundary for data that seemed impossible to separate just moments ago. So, when you put these two big ideas together, maximizing that margin for robustness and using the incredible kernel trick for flexibility, you get an algorithm that is just incredibly versatile and effective out in the real world.
And I mean, they're used all over the place. We're talking about things like face detection in your photos, text categorization for news articles, recognizing handwritten numbers on a check, all the way to really high-level science, like helping physicists discover new subatomic particles. It's just a huge testament to the power of these ideas.
So, you see, the big lesson here isn't just about a specific machine learning algorithm. The support vector machine teaches us something really profound about problem solving in general, that sometimes the most tangled, complex problems can become surprisingly simple if we can just find the right way to look at them. Thanks for watching.